700 meters beneath the Atlantic Ocean, there's a cluster of pale white towers rising out of total darkness. One of them nearly 60 meters tall, taller than a 15-story building. It looks like the ruins of a sunken cathedral. It has no volcano beneath it. It shouldn't be producing heat, energy, or life at all. And it was found entirely by accident, in the last hours of an expedition that was looking for something else completely. This is the Lost City Hydrothermal Field, discovered on December 4th, 2000, by a team of scientists aboard the research vessel Atlantis, led by geologist Deborah Kelly of the University of Washington, alongside Donna Blackman of Scripps Institution of Oceanography and Jeff Carson of Duke University. Their actual mission that day had nothing to do with finding a new ecosystem. They were there to study the structural geology of the Mid-Atlantic Ridge, the longest mountain range on Earth, 65,000 kilometers long, running down the middle of the Atlantic almost entirely underwater. What they found instead broke nearly every rule scientists thought they understood about deep-sea hydrothermal vents, and more than 2 decades of follow-up research still hasn't fully caught up to what it actually is. Let's start with what the team was expecting to find, because the contrast is exactly why this discovery landed as hard as it did. The Mid-Atlantic Ridge itself is almost entirely hidden from view, 90% of the largest mountain range on Earth sitting completely underwater, running like a seam down the middle of the Atlantic Ocean, along the boundary where tectonic plates are slowly pulling apart. As those plates separate, hot mantle rock rises to fill the gap, pressure drops, and some of that rock melts into fresh magma, which cools into brand new ocean crust in a process that repeats continuously, spreading the seafloor outward at roughly 2.5 centimeters per year, slow enough to seem trivial on a human timescale, fast enough to have widened an entire ocean basin over millions of years. First identified in 1853 and confirmed as a continuous underwater mountain range by the HMS Challenger expedition in 1872, the ridge wasn't fully mapped and understood as the planet-spanning feature it actually is until sonar surveys in the 1950s finally revealed its true scale. By 2000, hydrothermal vents were already a well-established feature of ocean ridges, structures scientists called black smokers, chimneys that spew dark, mineral-rich fluid heated by direct contact with magma near a volcanic ridge crest, typically running between 200 and 400 degrees Celsius. These vents were understood to require active volcanism directly beneath them, which is why scientists only expected to find them along the ridge axis itself, the specific line where new crust is actively forming. On the night of December 4th, in the ship's control van, geologists Gretchen Frew-Green and Barbara John were watching camera feed from a towed sled skimming the seafloor roughly 800 meters down, off the flank of an underwater mountain called the Atlantis Massif, 15 kilometers away from the ridge axis, on crust more than 1 million years old, a location where nobody expected any hydrothermal activity to exist at all. Then the screen filled with pale spires. The team had time for exactly one more dive before weather forced them back to shore. Diving in the submersible Alvin, they descended into a landscape unlike anything previously documented on the seafloor. Steep-sided pinnacles rising up to 60 meters tall, the tallest hydrothermal structure ever recorded at the time, surpassing the previous record holder, a black smoker chimney nicknamed Godzilla that stood roughly 45 meters before it later collapsed. But the towers weren't dark, sulfide-laden chimneys. They were pale, almost luminous, built largely from carbonate minerals and magnesium hydroxide, the same basic chemistry that forms limestone cave formations, not the iron and sulfur compounds that build ordinary black smokers. The temperatures were equally strange. Rather than the 200 to 400 degree fluids typical of volcanic vents, Lost City's chimneys discharge fluid around 75 degrees Celsius, with some flange structures trapping pools of water closer to 40 or 50 degrees. Warm, but nowhere near the volcanic furnace conditions scientists expected. As Duke geologist Jeff Carson put it at the time, if this vent field had been sitting on land instead of the ocean floor, it would have been designated a national park on the spot. The team named it the Lost City, and then their time ran out. Weather forced an immediate ascent, leaving them with more questions than answers, and no way to investigate further on that expedition. Here's why the discovery mattered so much once researchers had time to properly analyze what they'd seen. Everything about Lost City contradicted the established model of how hydrothermal vents form. There was no magma chamber underneath it. Instead, researchers determined the entire system was being powered by a process called serpentinization, seawater penetrating deep, ancient fractures, in mantle rock exposed by large geological faults, reacting chemically with a mineral called olivine. That reaction alone generates heat, along with hydrogen, methane, and highly alkaline fluid, all without requiring a single drop of magma anywhere nearby. When those chemically transformed fluids mixed back into cold seawater, calcium carbonate crystallized out of solution, slowly building the pale limestone-like towers the team had stumbled onto. The implications went further than just geology. Lost City went a step further. It showed life doesn't need volcanic heat either. The chimney walls were coated in thick biofilms of archaea, ancient single-celled organisms that don't breathe oxygen or rely on photosynthesis at all, but instead consume the hydrogen and methane produced directly by the rock-water reaction beneath them, essentially eating the chemistry of the planet itself. Around them lived swarms of tiny, translucent shrimp, snails, and amphipods, an entire ecosystem running on nothing but rock chemistry in one of the most stable, undisturbed environments on Earth. Follow-up expeditions gradually filled in what that single, rushed dive in 2000 couldn't answer. In 2003, the same core team returned aboard Atlantis, this time equipped with an autonomous robotic vehicle called ABE, capable of running pre-programmed survey routes to build high-resolution sonar maps of the site. Combined with 19 additional dives in Alvin, researchers mapped a full dozen vent structures spread across roughly a square kilometer, including a 4-tower complex nicknamed Poseidon standing nearly 61 meters tall. Isotope and radiocarbon analysis eventually revealed the field had been continuously active for at least 30,000 years, a number that was later revised upward dramatically to at least 120,000 years, based on detailed bathymetric mapping and direct observation of the structure's growth patterns. That number is worth sitting with. Lost City has been quietly running, unnoticed by anyone, for well over 100,000 years, making it the longest-lived venting environment ever documented anywhere in the ocean. For years afterward, one major question remained completely unresolved. Was Lost City a genuine, one-of-a-kind fluke, or were similar systems hiding elsewhere along the seafloor, simply never noticed? In search of an answer, NOAA and the Schmidt Ocean Institute launched a dedicated expedition surveying a full 700-kilometer stretch of the mid-Atlantic ridge, using shipboard mapping, chemical plume sensors, and a remotely operated vehicle equipped with real-time methane detection. The search turned up 3 entirely new hydrothermal vent fields, but every one of them turned out to be a conventional, volcanically powered black smoker system, not a second Lost City. The closest thing to a match arrived in 2017 at a completely different location, the southwest Indian Ridge, more than 3,000 meters down, where researchers found a genuinely serpentinization-driven system they named, with admittedly less imagination, the Old City. It shared Lost City's core underlying chemistry, but at that depth, the crushing pressure and different fluid dynamics prevented the growth of comparable 60-meter towers, producing something closer to a small chemical village than a full limestone metropolis. Then, in a separate expedition using one of the most sensitive methane detection systems ever deployed, researchers investigating a site called the Puy de Fol volcano, also along the mid-Atlantic ridge, picked up a methane and hydrogen signature that initially looked exactly like Lost City's chemical fingerprint. When their robotic vehicle finally reached the seafloor, they'd instead found another massive black smoker field entirely, with vents blasting fluid at 340 degrees Celsius, hot enough to melt lead. The first vents discovered along that specific 40-year unexplored stretch of ridge, but still not the twin researchers were hoping for. Most recently, in 2023, the International Ocean Discovery Program drilled directly into the southern wall of the Atlantis Massif. Reaching more than a kilometer below the seafloor, the deepest borehole ever successfully completed in this specific type of mantle rock formation, pulling up a continuous core sample of the altered upper mantle feeding the entire system, giving researchers their most direct physical look, yet at the rock actually driving Lost City's chemistry from below. So here's where the honest picture of Lost City actually lands, more than 2 decades after that accidental discovery. Every major follow-up expedition since 2000 has made the story more complicated, not less. Researchers now understand the underlying chemistry driving the towers, serpentinization rather than volcanism, considerably better than the original discovery team did in that single rushed dive. They've confirmed the system has been running continuously for over 100,000 years, and they found a genuine chemical relative on the opposite side of the world. But despite deliberately searching hundreds of kilometers of ridge with increasingly sophisticated tools specifically built to find another one, nobody has found a second true Lost City anywhere on Earth. It may be genuinely, functionally unique, the product of an unusually precise combination of exposed mantle rock, low sustained heat, and enough uninterrupted time for towers this size to form and survive, a combination rare enough that decades of dedicated searching still hasn't turned up a proper match. That uniqueness carries real scientific weight beyond Earth itself. Because Lost City proves life can run entirely on rock-water chemistry, without sunlight and without volcanic heat, it's become a genuine reference point for astrobiologists studying Jupiter's moon, Europa and Saturn's moon Enceladus, both of which are believed to hide liquid oceans beneath thick ice shells, sitting above rocky cores capable of producing the exact same kind of chemistry. The connection isn't a speculative decoration. Both Europa and Enceladus are believed to have rocky mantles in direct contact with liquid water, sealed away from sunlight by miles of ice, essentially the same fundamental setup that powers Lost City, just relocated to a different moon entirely. NASA and other space agencies studying these icy moons have directly cited Lost City's chemistry as a working model for what a habitable environment without sunlight might actually look like in practice, rather than as a purely theoretical possibility. If serpentinization can generate enough chemical energy to sustain an ecosystem of archaea and shrimp for over 100,000 years on Earth, the same basic physics operating inside an ice-covered ocean moon becomes a genuinely serious candidate for hosting life elsewhere in our own solar system. Not as scientific optimism, but as a direct, testable analogy sitting on our own ocean floor. What's left today is a genuinely unresolved frontier, rather than a settled discovery. Lost City is still slowly growing, fractions of a millimeter at a time, and it now faces a very modern threat. Deep-sea mining interests have begun eyeing the mineral-rich crust surrounding vent systems along the mid-Atlantic ridge, and scientists have warned openly that commercial extraction near sites like this risks destroying a system that took over 100,000 years to build, before researchers have even finished understanding what it's actually telling us about how life might begin here or anywhere else. So we want to ask you directly. If a discovery this significant was found completely by accident, on the very last dive of an expedition that almost didn't happen, what do you think is still sitting undiscovered on the 70% of this planet we've barely mapped at all? Leave your thoughts in the comments below. We read every one of them. If this is the kind of story you want more of, the kind where the real discovery is realizing how much of our own planet remains genuinely unexplored, make sure you're subscribed, because next time, we're heading somewhere just as remarkable. Until then, stay curious and keep questioning the version of history you were handed